All right, so today we're going to be starting chapter 23. This is the chapter on electric potential. Today we're going to be focusing on potential energy, work, and an introduction to electric potential, and we'll do more calculations with electric potential tomorrow. All right, so the first thing is potential energy. So we remember from Physics 7c that in the case of gravity, when you have two masses that are near each other, there's a potential energy associated with those two masses, with that system of masses. And we have the exact same thing in electrostatics. When we have two or more point charges, or any shaped charges actually, any charged objects near each other, they're going to have a potential energy associated with that charge distribution. So before we get into it, let's just review potential energy and work, since we are going to be using that a lot today. So remember that potential energy, denoted by U usually, is a scalar. So it's very important in this chapter, since we're going to be using both scalar functions and vector functions. It's very important to keep track of and be conscious of what is a scalar and what is a vector. So potential energy is a scalar. It doesn't have any direction. It's just a number. And it's measured in joules. And then work is also a scalar, and it's also measured in joules. And remember from 7c that work is the dot product between force and displacement for a constant force. So if we have a force of just 5 newtons in the x-hat direction, that's a constant force, and you would just dot your force into your displacement vector. But when we have a variable force, like the electric force, because our electric force from Coulomb's law, remember, has that r squared on the bottom, so it's going to be variable as you move throughout space. When we have a variable force like that, we have to integrate. And just a quick reminder with our dot products. So just recall, when we have our force and displacement in the same direction, that means our cosine is 0 degrees and we get a positive 1. So the work done when our force and displacement are in the same direction is always positive. Now, if it's perpendicular, so let's say our force, this is our force and our displacement. If our force and our displacement are perpendicular, that means that our cosine now is 90 degrees, and cosine of 90 is 0. So if our force and displacement vectors are perpendicular, no work is done. And then if they're in opposite directions, so if our force and displacement are opposite, our cosine here is 180 degrees, and cosine of 180 is negative 1. So when our force and displacement are in opposite directions, our work done by that force will always be negative. All right, now let's review conservative forces. So we're going to talk a little bit in more detail about conservative forces tomorrow and how it relates to Maxwell's second equation. But for now, just remember that a conservative force means that the work done by that force is independent of your path taken. So gravity is your classic conservative force, because if you have like a book or something and you move it from here to here, the work done only depends on your endpoints. It doesn't matter if you zigzagged it or whatever you did with it. The point is that it only matters your starting point and your end point. And all conservative forces are like that. Friction is an example of a non-conservative force, because friction, it does matter what path you take. And so this characteristic of conservative forces, being path independent, means that the work done by a conservative force over a closed path is always 0. So if I just start at this point and I go around in a circle here, that means my work done, if I'm looking at a conservative force, will always be 0. So this is very, very important. This we'll come back to this tomorrow, as I said. So the electrostatic force is an example of a conservative force. Now be careful though, because when we get into later chapters where we're not in electrostatics anymore, the electric force is no longer conservative. So when we have time-varying electric fields, those forces are not necessarily conservative, but electrostatic forces are always conservative. Okay, now a review of the work-energy theorem. So recall again from 7c, I'm sure you've seen conservation of energy. So if only conservative forces are acting, our initial kinetic plus initial potential energy will be equal to our final kinetic plus final potential energy. So we'll be using this a lot, obviously, in this chapter especially. And the work energy theorem states that the work done is equal to the change in kinetic energy. So this is kinetic energy final minus kinetic energy initial. And then the work done is also equal to the negative change in potential energy. So this will be negative U final minus U initial. All right, so those are all of our little reminders from 7C that we'll need for this chapter. So now let's get into the work done by an electric force. So before we look at this integral, let's say we have a positive charge sitting at the origin. So we've got a positive charge sitting at the origin. It's emitting an electric field, in all directions. And we want to know if we take another positive charge in from infinity, so let's say this is out at infinity. If we take another positive charge from infinity and we try to move it from infinity to some distance, let's say r. So let's say we want to move it to some distance r away from this other positive charge. How much work is the electric field doing in that situation? Well, we know we're going to have to integrate because we have a variable force, right? So we're going to be integrating. The force is the electric force, which is just given by Coulomb's law here. So we just have the 1 over 4 pi epsilon naught, Q1, Q2. We'll call this one Q1. This one will be Q2. And then we have r squared. So again, I use the prime notation to denote our r, that's our variable of integration, compared to our r, which is the distance we're moving that charge to. So we're integrating our force, and then we're integrating it from infinity to r. Now I know that might look weird to some of you, but really what I'm doing here is a line integral. And when you do a line integral, you integrate from your starting point to your ending point. So I'm starting at infinity, and I'm moving to some distance r. So I'm going to be integrating from infinity to some distance r away from the origin here. So let's just do this integral. So we know how to integrate here. The only r we have is on the bottom. We have this r squared on the bottom here. So all of this will be constant. So if we want to just integrate 1 over r squared, that will give us negative 1 over r. So now we just have our constants out here. We have negative 1 over r. We want to evaluate it at that distance r and infinity. So we get negative 1 over r. And then remember, this would be 1 over infinity, and 1 over infinity is just 0. So this integral ends up being, we have the negative here, it's just negative 1 over 4 pi epsilon naught, Q1, Q2 over r. So this is the work done by the electric force if this particle here moves towards this particle against the electric field created by this particle at the origin. So now remember that this means that an outside force like you or I would have to do the opposite amount of work. So if I physically wanted to move this charge from here into here, I would have to do negative, negative, which is a positive amount of work, to move that charge from infinity to r. And you can think of it because two positive charges don't want to be near each other, right? They want to repel each other. So if I want to bring two charges that are trying to repel each other close together, I'm definitely going to have to do positive work. I have to put energy into that system because they don't want to be near each other. They want to repel. So I'm going to have to do positive work to bring those two charges close together. Okay, so just to draw this out a little bit better, so I have my two charges here, and I have some distance r here. And I want to move this positive charge to this point here, which is a distance r away from my origin. So this charge, this positive charge at the origin, is emitting an electric field. I have to do positive work against that electric field in order to move this charge in closer. So the external work is positive and will be equal to the 1 over 4 pi Q1 Q2 R. And then the electric field will be doing, so I'll just call that W E. So the electric field will be doing negative work. And so your work done by your electric force and the work done by an external force will be equal in magnitude, but opposite signs. And this is the same for gravity. If gravity does positive work in some situation, the external force, if I'm like moving a book up and down, if gravity does positive work, I do negative work. If I do positive work, gravity does negative work. So it's the exact same thing here with your electric force and some external force, like a person moving a charge. All right, so we said that the work done, so let's just figure out what the potential energy is now from the work. So we said that the work done by the electric force is equal to negative change in potential energy. And the negative change in potential energy is given by UF minus UI. And now in our previous example, where we had this charge way out at infinity, right? We said we're bringing another charge in from infinity and we're bringing it closer. We can just assume that our potential energy is 0 out there. So let's just say that our initial potential energy is 0. And now the reason we can do that is the same as in gravity. Remember when you did gravitational potential energy problems, you could pick your 0 of potential energy to be anywhere, right? You could pick it on the ground, you could pick it on the top of a building, wherever you wanted, because only differences in potential energy mattered. So we can do the exact same thing here. So I'm just going to say, well, when my particle was way out in infinity, my potential energy was 0. And that's just where I'm calling my 0. So that's totally fine, and we'll do more problems with that later today and tomorrow. So now I just have my final potential energy left. So I just have the work done by the electric force is negative UF. And remember, we said that the work done by the electric force was this, right? Negative 1 over 4 pi epsilon naught Q1 Q2 over R. So I can just plug this right in to my work, and I get that negative 1 over 4 pi epsilon naught is equal to Q1 Q2 over R is equal to negative UF. Can cancel out my negative signs. And now I have my potential energy of my two particles. So this is how we write our potential energy between 2 point charges. And it's important to remember here that we're talking about point charges. So we have 2 point charges separated by some distance r. This is going to be the potential energy between them. And now 2 important things to keep in mind. As I mentioned earlier, potential energy is a scalar. And also be careful that it has a 1 over r dependence. So all of the things we've seen for the electric field so far have had like a 1 over r squared. But what we're doing today is going to involve a 1 over r dependence. So be really, really careful, especially on exams, that when you're doing potential energy, you make sure that it's only 1 over r for your potential energy. All right, so let's do an example with this, what we have so far. Okay, so for this example, we have a positron, which is the antiparticle of an electron, has mass 9, so let's just write our variables down. So we have the mass of the positron is 9.11 times 10 to the negative 31 kilograms, and a charge equal to that of the electron, but opposite in magnitude. Suppose a positron moves in the vicinity of an alpha particle, which has charge twice that of the fundamental unit of charge, so 3.2 times 10 to the negative 19 coulombs, and a mass, so the mass of our alpha particle is 6.64 times 10 to the negative 27 kilograms. The alpha particle's mass is more than 7,000 times that of the positron, so we assume that the alpha particle remains at rest. When the positron is 1 times 10 to the negative 10 meters from the alpha particle, it is moving directly away from the alpha particle at 3 times 10 to the 6 meters per second. So we have our alpha particle here. Actually, so we have our alpha particle here, and it's positively charged. And then our positron is over here, and it is moving directly away from the alpha particle. Okay. We want to know, what is the positron speed when the particles are 2 times 10 to the negative 10 meters apart? So let's do this first. So we're going to have to use the work energy theorem here. All right, so the way we're going to do this is let's use conservation of energy since we don't want to do an integral yet. So we know that the kinetic energy initial plus potential energy initial is going to be equal to kinetic energy final plus potential energy final, since we have only conservative forces acting here, namely the electric force. So our initial kinetic energy of the proton is the positron, the mass of the positron, times the velocity, the initial velocity squared. All right, so let's plug some things in here and find the initial kinetic energy. So we have 1/2, the mass of the positron is 9.11 times 10 to the negative 31. The initial velocity is 3 times 10 to the 6 meters per second, and we're going to square that. So this comes out to 4.10 times 10 to the negative 18 joules. So this is the positron's initial kinetic energy. Now let's look at the initial potential energy. So the initial potential energy will be given by this, the charge of the positron, charge of the alpha particle, and the distance between them initially. So we'll call that Ri. So this, the charge, we have 1.6 times 10 to the negative 19. And then we have 3.2 times 10 to the negative 19 divided by the initial distance between them. The initial separation is 1 times 10 to the negative 10. So this initial potential energy comes out to 4.61 times 10 to the negative 18 joules as well. All right, so we have our initial energies. So now we can find in the exact same way, since we know their final separation is 2 times 10 to the negative 10 meters, we can find their final potential energy, and then we can just solve for the final velocity here. So let's do that. So let's find the final potential energy, 1 over 4 pi epsilon naught, the charge of the positron, charge of the alpha particle, and then the final separation that we're looking at. So we'll have 9 times 10 to the 9 is the 4 pi epsilon naught, and then we have 1.6 times 10 to the negative 19, 3.2 times 10 to the negative 19 for the alpha, and then their final separation is 2 times 10 to the negative 10 meters. And this comes out to 2.3 times 10 to the negative 18 joules. So now let's just write this all out. So our initial kinetic energy was 4 times 10 to the negative 18 joules. So we have 4.1. The initial potential energy was 4.61 times 10 to the negative 18 joules. And this will be equal to the final kinetic energy plus 2.3 times 10 to the negative 18 joules for the final potential energy. So now we can just move this over to this side, add up everything, and we solve for the kinetic energy on this side here. we get that the final kinetic energy is equal to 6.41 times 10 to the negative 18 joules. Okay, so now we have the final kinetic energy of our positron when it's now 2 times 10 to the negative 10 meters away from the alpha particle. So now that we have the final kinetic energy in joules, we can just use the formula. We know that this is equal to 1/2 the mass of the positron times its final velocity, right? So now we can just set this equal to each other. We know the mass, and we can just solve now for the velocity. So we have 6.41 times 10 to the negative 18 is equal to 1/2. The mass of the positron was 9.11 times 10 to the negative 31, and VF squared. So multiply both sides by 2 to get rid of your 1/2. Divide both sides by 9.11 times 10 to the 31. And you get, when you solve for VF, you get that VF squared comes out to 1.4 times 10 to the 13, and then take the square root. So we'll take the square root, and we get that VF is equal to 3.6 times 10 to the 3.8 about, times 10 to the 6 meters per second. And so this is how fast our positron is moving when it's now a little bit further away from the alpha particle. And this makes sense because this is faster, right? Here we have 3.8 times 10 to the 6 meters per second. And initially, it was only moving at 3 times 10 to the 6. So it's sped up, which makes sense because we have a force acting on it in the direction that it's moving, so we would expect it to speed up. All right, so all we did here was just use conservation of energy and our formulas for kinetic and potential energy to find that final velocity. All right, now let's do part B. So part B, what is the positron's speed when it is very far from the alpha particle? So what that means is they're just saying what is the positron speed when it's basically at infinity compared to the alpha particle. So they want you to take the distance to infinity. So we're going to do the exact same thing where we have the initial kinetic, the initial potential, the final kinetic. We're looking for that final volume, so we need to find the final kinetic energy first, plus the final potential. Now for the final potential energy, they said that the particles are very far away, so we can assume that R is infinity. And so when we have Q1, Q2 over R, and R is infinity, that just means 0. So our final potential energy is just 0. So we're going to do the exact same thing. We have our initial kinetic was 4.10 times 10 to the negative 18. Our initial potential was 4.61 times 10 to the negative 18. And then we have our final kinetic we're looking for. And then this is just 0. So we can just add up these two numbers right here, and we get 8.71 times 10 to the negative 18 joules is equal to our final kinetic energy. And so again, we just have 1/2 m positron VF squared. We know the mass of the positron. And we're just going to solve for VF here. So get VF by itself, take your square root, and you will get for that the final velocity is 4.4 times 10 to the 6 meters per second. Okay, so this is the final velocity it reaches once they're infinitely far apart. Now for part C and D, I just took this example out of your book, so the book works through parts C and D. So definitely try reworking this with one of the charges where the positron is actually an electron, and see if you can understand how that situation will change if now you have a positive and a negative charge instead of two positive charges. All right, so now let's look at the case of multiple charges. So now let's say we have a configuration of three charges. So we have initially Q1, Q2, and Q3. Now we want to know what is the potential energy associated with bringing in a fourth charge, Q0, and placing it at this point A. So this point A is a distance R1 from Q1, a distance R2 from Q2, and a distance R3 from Q3. So what is the potential energy associated with that? Or another way to think of that is how much work do I have to do against the electric field of Q1, Q2, and Q3 together, that total electric field? How much work do I have to do to bring in this charge from infinity and place it at this point? Well, we know if we just had, let's say, just Q1 here, and we wanted to bring in Q0, we know how to do that, right? That would just be 1 over 4 pi epsilon naught Q0 Q1, and then the distance would just be R1. That would be it, right? But now we also have charge 2. But we know what we would do if it was just Q0 and Q2. We would just have the exact same formula, but we would have Q0 and Q2 instead, and the distance between those. And the same thing for charge 3. If it was just charge 3 we were looking at, we would know exactly how to write it. It would just be the potential energy between Q0 and Q3. So the potential energy adds, just like the electric field added, the total potential energy will just add. So all we have to do, if we want to figure out what is the potential energy associated with bringing in Q0 to this configuration that's already there, all we have to do is just add up the individual contributions. So I can rewrite this here in a slightly more nice way. I can factor out my 1 over 4 pi epsilon naught. I can factor out a Q0, right, because Q0 is in every term here. And then I can just write it as Q1 over R1 plus Q2 over R2 plus Q3 over R3. And now I can still write it in an even nicer, simpler way. I can write this as a sum. So I can write this as 1 over 4 pi epsilon naught, Q0, and then I can write a sum like this. So I can rewrite my total potential energy associated with bringing this charge in as a sum over the existing charges. And now, as you might be able to guess, you can write it like this for any number of charges. So no matter how many charges I had, if I had 100 charges sitting there already, I would just add up the contribution from each individual charge with my Q0. So the potential energy associated with a specific charge Q0 located at some point A is the work required to bring in that specific charge from infinity and bring it into that location against the electric field that's been set up by those other charges. And we can write that as a sum over those other charges. So each of these Qi's are already sitting there, and we're bringing in that extra Q0. So now be careful, because this isn't the total potential energy associated with the entire system. It's just the potential energy associated with bringing that one charge in. So this is just how much work did an external force that I have to do against the electric field set up by these charges. How much work did I have to do to bring this charge in and place it at a distance r sub I from each of these charges? Okay, but now let's find the total potential energy of the entire system. So what if I wanted to find out, well, how much work would I have had to do to assemble this entire system? So if I wanted to place charge Q naught here, and then bring in charge 2 and place it here, and then bring in charge 3 and place it here, and then bring in charge Q naught and place it there, how much work would I have had to do to assemble that configuration of charges? Well, you can kind of do it the same way that we just did, but you're going to have to do each pair of charges. So let's pretend we just have Q naught and nothing else. So it will take me no work to just bring in a single charge if there's no existing electric field in that region, right? Because if you're moving a charge in a region with no electric field, you're not working against any force, so there's no work associated with that. So no potential energy. So to bring in this first charge requires no work. But if I want to now bring in my second charge Q2, it's doing, I would have to do work against the electric field of Q1. And then they're going to have some distance between them. So there's a potential energy associated here. Now if I want to bring in charge 3, well, now I would have to do work against both Q2 and Q1. And now if I want to bring in charge Q naught now, well, now I'm doing work against Q1, Q2, and Q3. So you have to add up the potential energies associated with every pair of charges. So if I were to write the total potential energy for this setup, I would have to write my total potential energy. I'll just bring out my 1 over 4 pi out here. I would do my potential energy between, let's say, Q1 and Q naught. So we'll do Q1, Q naught. We'll start with Q naught first. So Q1 and Q naught, that distance R1. Let's call that the distance between 1 and naught. Now I would have to do, so then I would have the pair Q naught and Q2 and the distance between them. Then I would have the pair Q naught and Q3 and the distance between them. And then I would have to do Q1 and Q2. So then plus Q1, Q2 and the distance between them. Then Q1 and Q3, the distance between them. And then my last pair would be Q2 and Q3. Q2 and Q3. And those are all of my combination of pairs of charges without double counting, right? So if you count, charge 1 and charge 3, I don't then need to count charge 3 and charge 1. So you want to add up all of the potential energies between each pair of charge without double counting those pairs, since the order doesn't matter. And that will give you the total potential energy of assembling the entire system. So you just want to add up the potential energies between each pair of charges, and you will get your total potential energy for the entire system. So you can also write this as a sum, and I know this sum might look scary, but all this sum is saying is just what we just did. So we have our Qi and Qj are just two different charges. R sub ij is just the distance between those two different charges. And then this sum of I is less than j just means that you're not double counting your sums. So it just means if you do charge the sum for charge 1 and charge 2, you don't then need to add the sum for charge 2 and charge 1. You already counted that. Okay, so let's do a simple example with this. All right, so here we have point charges fixed on the x-axis. We have Q1 at x equals 0 and charge negative e. We have charge 2 of positive e fixed at x is equal to a. Now we want to find the work that must be done by an external force, so not the electric field, by like me, to bring in a third point charge, Q3, so that's here, of positive e, from infinity to the point x is equal to 2a. All right, so how much work do I have to do to assemble that scenario? Well, for part A, it would just be the potential energy of Q3 and Q1 and the distance between them, plus the potential energy between charge 3 and charge 2. And we have the distance between them there. So I'd only have two contributions because I'm only saying how much work do I have to do to bring in a single charge against the electric field created by these two pre-existing charges. So we just have two contributions there. So let's write this out. We have Q3 is E, Q1 is negative E, and the distance is 2A. Then we have Q3 is E, Q2 is positive E, and the distance there would just be A. And this will come out to 1 over 4 pi epsilon naught. We have a negative E squared over 2A plus E squared over A. So you can leave it that way, that's fine, or you can simplify it and write it as E squared over 8 pi epsilon naught A. So that's how much work I have to do, and this is in joules. That's how much work I have to do against the electric field of these two charges to bring in this third charge and place it at a location x is equal to 2A. Now, the total potential energy of the system of these three charges. So when you see total potential energy, that means how much work did I have to do to bring in the first charge with nothing else there, bring in the first charge, then bring in the second charge, then bring in the third charge. So how much work is required to assemble the system? So for that, you're going to need to add up the contribution from each pair of charges without overcounting or double counting. So our potential energy will be, factor out the 1 over 4 pi epsilon naught. So all of our pairs of charges will be Q1 and Q2, the distance between them, Q1 and Q3, the distance between them, and then Q2 and Q3 is my last pair and the distance between them there. Okay, so now let's plug things in. So I've got all of my pairs, didn't double count anything. So Q1 is negative E, Q2 is positive E, our distance is A. Q1 is negative E, Q3 is positive E, our distance is 2A. And then Q2, positive E, Q3, positive E, and the distance is A. So this simplifies to negative E over A, E squared, minus E squared over 2A plus E squared over A. So now all of this will simplify to negative E, 8 pi epsilon A. So it actually takes negative work to assemble the whole system. All right, so this is like a simple example with just 3 charges. On an exam, I would never ask you to do something with more than like 3 or 4 charges at the most. I'd never ask for something with like 10 charges, so you'd never have that many pairs to add up. Okay, so this is electric potential energy. So now let's move on to electric potential. So just as the electric field can be thought of as the force per unit charge, remember the units of electric field were newtons per coulomb, so we can think of it as a force per unit charge. We can define the electric potential as the potential energy per unit charge. So our electric potential, we're going to denote as V, and it's measured in volts. Our potential energy is in joules, is denoted U, and the charge here in coulombs is Q. So we have this new quantity called the electric potential, which we can write in terms of the potential energy and the charge. So our electric potential can be thought of, like I said, as the potential energy per unit charge. And we're going to see in our next lecture why the potential is such a useful tool in electrostatics. Now, just be really careful here. because I know potential and potential energy sound like they should be the same thing, but they're not. I know it's very unfortunate wording, but that's the way things happen. So be really careful when you're doing problems. Electric potential and electric potential energy are two different things. So we can divide our potential energy function, divide out one of the charges, and we'll be left with the potential of a point charge. So now we're going to talk more about potential tomorrow, but for now you can just sort of take as a given that a point charge will have a potential given by this formula. So we have the 1 over 4 pi epsilon naught, we have the value of the charge, and then we have the distance from that charge. So if you have a point charge anywhere in space, there'll be a potential function associated with that point charge. And potential adds just like potential energy did, where if we have a collection of point charges, we can find the potential energy per unit charge by just adding up all of the individual potentials. So let's just get a little bit more of a conceptual understanding of what potential looks like. So if you have a positive point charge, the potential will decrease as you move away. So the potential energy per unit charge in this space will decrease as you move away from the positive point charge, and it will increase as you move inward. And if we were to plot the potential for this positive point charge, it would look like this, where this is proportional to 1 over r. So the potential gets very, very high as you're close to the positive point charge, and then goes off to 0 as you get farther and farther away. And you can think of that because if you have, let's say, another positive test charge that you bring in, these two charges don't want to be near each other. So when they're near each other, they have a very high potential energy because there's a lot of energy associated with two positive point charges being very close to each other. And then there's no potential energy associated with them if they're infinitely far apart. So this positive point charge, this positive test charge, would want to move away from the other positive charge. It would want to go out to infinity, where the potential is lower. And now the opposite is true when we have a negative point charge. So if we have a negative point charge here, the electric field points inward, and that means that the potential decreases as we move towards a negative charge and increases as we move away from a negative charge. Because if we put a positive test charge in this location, it would want to get as close to that negative charge as possible. It would want to go to its lowest energy configuration, which would be very, very close to this negative charge. They're attracted to each other. So the potential for a negative charge looks like this. So the potential for a negative charge actually looks like this. So the potential is very, very low as you're close to a negative point charge, and then it has an asymptote as you move farther and farther away. Okay, so let's just do one example and then we'll be done for the day. So let's look at the potential for an electric dipole. So I mentioned earlier that a dipole is just a positive and a negative charge close together. We'll talk about them more in chapter 24. But we just have a positive and a negative point charge separated by some distance here. So we have charge Q1 is 12 nanocoulombs, and charge Q2 is negative 12 nanocoulombs, and they're 10 centimeters apart. We want to calculate the electric potential at point A, point B, and point C. So the electric potential of a single point charge is just given by this. And remember, we can just add up individual potentials to find the total potential at any point. So at each point, we're just gonna, add up the individual contributions from charge 1 and charge 2, and that's it. So let's do for point A. Our total potential will just be the contribution from Q1. So we've got Q1. And the distance from Q1 to point A is just 6 centimeters, as we can see here. So let's put in Q1 is just 6 centimeters. And then we add up the contribution from Q2. So Q2 is 4 centimeters from point A. So let's plug some numbers in. I'll factor out my 4 times 10, I'll factor out my 4 pi epsilon naught. Q1 we said was 12 nanocoulombs. And then we have 6 centimeters. Q2 was negative 12, so that will be a minus nanocoulombs. And that was 4 centimeters. So we just plug this into our calculator, and for point A, we get, this comes out to negative 900, and our units are volts. So at point A, the potential is negative 900 volts. And you can see that this makes sense because if we were to place a positive test charge at location A, it's much closer to the negative charge than it is to the positive charge. So we would expect it to have a negative potential there because it wants to go closer to the negative charge. Now when we do location B, we can expect this to be a positive potential over here because if we were to place a positive test charge, it's much closer to this other positive charge and it does not want to be there. So there's going to be a higher potential energy associated with that location. So let's do location B. So for location B, and let's just move this. All right, so let's do location B. So at location B, we can just add up our contributions from each charge again. So the total potential will be Q1 is a distance now of 4 centimeters from location B, so that will be 0.04. We'll just keep it at 4 centimeters for now. Then Q2 is now a distance of 10 plus 4, so it's now 14 centimeters from location B. And now we can just add those up, plug in some numbers. We've got 9 times 10 to the 9. Q1 was 12 nanocoulombs. Q2 was negative 12. And this was 14 centimeters. And we just add up those numbers and you get, for location B, it comes out to 1,930 volts. All right, and now let's do location C. So location C, just going to add up the contributions again. So we get 1 over 4 pi epsilon naught. Now from charge 1, point C is 13 centimeters away. So we just have Q1 is 13 centimeters. Q2 is the same distance. So you can kind of see what our potential is going to end up being at point C. So let's plug in our numbers. So Q1 is 12 nanocoulombs. Q2 is negative 12 nanocoulombs. And you can see now that these two terms will cancel out, right? We have the 12 times 10 to the negative 9 over 13 minus 12 times 10 to the negative 9 over 0.13. So our potential at this point is just 0. And this will actually be true on the entire line between charge 1 and charge 2. So this entire line that's equidistant between our two point charges will have a 0 potential. Okay, so that is it for today. Next time we will learn how to calculate the potential from the electric field and from different charge distributions. So I will see you guys then.
most holiest shrine.